Hello students, today we will discuss on unit 1.5.1 in the topic electric and magnetic circuits. The subject name is basic electrical and electronics engineering. In that, today we will understand about mutually induced EMF and its coefficient. Myself, Chandrasekhar S. Patil, Sharad Institute of Technology, Polytechnic, Yadrao. Before commencing with the today's topic, we will review or we will revise through the previous presentation wherein we understood about induced EMF, dynamically induced EMF, statically induced EMF, self-induced EMF and magnitude and coefficient of self-induced EMF. Induced EMF. So, whenever changing magnetic flux comes in contact with a coil, then an EMF is induced in the coil, and if we create a closed circuit, then the current flows through the circuit. That is called as induced current. Similarly, we have understood about dynamically induced EMF. Dynamically induced EMF is that EMF wherein the coil is moving in the magnetic flux, and due to the cutting of the magnetic flux by the moving coil, an EMF is induced in the coil, and because of that we have an induced EMF that is called as dynamically induced EMF. Statically induced EMF. Statically induced EMF is that EMF wherein we are the coil is stationary, whereas there is moving or changing magnetic flux. Because of that we have an EMF induced in the coil that is called as statically induced EMF. The best example for dynamically induced EMF is a DC generator, whereas for a statically induced EMF the best example is a transformer. Then we understood about self-induced EMF or inductance. What is self-induced EMF? Self-induced EMF, if you consider a coil C and we are passing the current through the coil, which is solenoid coil. If we pass a current through the coil, then what happens? We have got an induced EMF. That EMF which is induced is called as self-induced EMF, and the direction of the self-induced EMF is minus, means it is in the opposing direction, which opposes the change in current, because of which the magnetic flux is produced. It opposes the change in magnetic flux, or it opposes the current which is changing frequently and which is varying frequently, and because of that varying current there is a varying magnetic flux, and a self-induced EMF is the direction of the induced EMF is in the opposing direction, which is creating the EMF. That is called as self-induced EMF. Similarly, we understood about magnitude and coefficient of self-induced EMF. So we have understood that how the self-induced EMF, what is the magnitude and what is the coefficient of self-induced EMF. Today we will understand about factors affecting the inductance of a coil, mutually induced EMF, magnitude of mutually induced EMF, comparison between self-induced EMF and dynamically induced EMF, coefficient of mutual induction and dimensions of the coil, and coefficient of coupling. First we will understand the factors affecting the inductance of a coil. It is known that the inductance is proportional to the square of the number of turns of the magnetizing coil and is inversely proportional to the reluctance. The reluctance in turn depends upon the dimensions of the coil, that is its length and the cross-sectional area, and the relative permeability of the surrounding medium. So here we have clearly understood that The inductance is proportional to the square of the number of turns. If the number of turns is n, then the square of the number of turns will indicate the inductance of is proportional to the inductance of directly proportional to the square of the number of turns of the magnetizing coil and is inversely proportional to the reluctance. In this context, following points are worth noting. It is worth to note the following points. First one is, due to high relative permeability of iron and iron cored oil always has more inductance than similar air cored coil or coil with non-magnetic core. So, here it is clear that if there is a iron core, a ferromagnetic material is there which links the magnetic flux from one region to another, one magnetic flux to another magnetic flux. If there is, then the permeability of the medium will be high at the higher side compared to air medium or other non-ferromagnetic material. If you keep a ferromagnetic material in between the flux linking between the two coils, then it is called as dynamically mutual induction, and also we have the permeability increases or the efficiency of the transfer of flux from one coil to another coil is more in that case. For air or other non-magnetic materials, relative permeability is always constant and mu r is equal to 1. The relative permeability for air or vacuum medium or non-magnetic materials, it is always 1 or unity. Hence, the inductance of a coil with the core of air or other non-magnetic material is always constant and is independent of the value of the current. So, in this case, we have understood that the relative permeability of the non-magnetic material is always constant and it is unity and is independent of the value of the current. Whatever may be the current value, the permeability will be unity and it will not differ with the changing current. In the case of an iron core coil, the relative permeability of iron is not constant but varies with the current due to the saturation effect. As such, inductance of a coil also varies with the current. So, here it is worth noting that if the relative permeability of iron is not constant, okay. So, as we have understood in the hysteresis law, the relative permeability here will be of iron is not constant and but varies with the current due to saturation effect. It due to the saturation of the magnetic material or the ferromagnetic material, the relative permeability is not constant and it is varying. As such, inductance of a coil also varies with the current. Similarly, with the varying current also, the inductance of the coil varies. The inductance being dependent on number of turns, the inductance of a coil is greater than the inductance of a straight conductor of the same length. So, if you wound the ferromagnetic material on a conductor, then the magnetic inductance will be more in case of that wound coil than of a straight conductor. Okay, is greater than the inductance of a straight conductor of the same length. If you consider a conductor of 10 meters and it is wound on a material, and similarly, if you consider a 10 meter straight conductor, the inductance of the wound conductor will be more compared to the inductance of a straight conductor. If the conductor is bent back on itself, the field flowing due to the current flowing in one direction neutralizes that due to the current flowing in the opposite direction. Hence, the inductance is 0 under such condition. If the conductor is bent back, for example, see here, one direction from left side to right side, we are wound the copper conductor or the coil. Then we are taking bent back to the on the same turns to the from right to left. Then the current from left to right and the current produced due to the inductive effect from the right to left will neutralize, because the direction of current flowing in the left to right wound coil and right to left wound coil mutually neutralize or cancel each other, and hence the inductance is zero under such condition. Mutually induced EMF. Consider two coils A and C placed side by side as shown in the figure. The coil A is connected in series with a switch, a battery B and a variable resistor R. A sensitive galvanometer is connected across the coil C. Similar to statically induced EMF, we have here two coils. In one of the coils is the coil A and the other is the coil C. In one of the coil A, there is a switch, battery and a varying resistor. Whereas in the second coil, we have the galvanometer. In the coil wound, that is second coils, there is a galvanometer across the coil C. On closing the switch, let the current flowing in the coil A be I1 amperes. Okay. So whenever you close the switch, the current flowing through coil A is I1 amperes. Due to this current of the coil A will have its own flux. So because of the self-induced EMF, we have the coil A producing the flux, and that is because of the I1 amperes, we have the flux produced in the coil A, which will be having its own flux, and that is also called as self-induced EMF. Some of the flux produced by this coil will also link with the coil C. If now the current in the coil A is changed by varying R, it will change the flux linking with the coil C. So here in this case, in the coil A, we have the magnetic flux produced. The same flux is linking with the coil C. So because of that, what happens? We have the linking between the fluxes of coil A and coil C. So if you vary the resistor and change the current flowing through the coils, then the magnetic flux will also change accordingly. And then because of that, what happens is we have the changing flux linking with the coil C. According to Faraday's, some of the flux produced by this coil will link also with coil C. If now the current in the coil A is changed by varying R, it will change the flux linking with the coil C. According to Faraday's law, this changing flux linking with the coil C will induce an EMF in it. The production of the EMF will be indicated by the deflection of the galvanometer. So in this case, whenever this flux is linking with the whenever this flux is linking, coil A is linking with C, the changing flux due to Faraday's law of electromagnetism, we have understood that there is a EMF induced in the coil C, and that because of that a galvanometer deflection is seen, which is also indicates the flow of current in the coil C. So we have understood that by varying the flux due to varying the resistor, coil linking with magnetic flux linking with coil C will generate an EMF across the coil C, and that is seen with the help of galvanometer, showing the deflection in the galvanometer. Okay. Thus, any change of current in the coil A will produce an EMF in the neighboring coil C. This phenomenon is known as mutual induction. So, because of the change in current in the coil A, an EMF is generated in the neighboring coil C. Okay, and this phenomenon is known as mutual induction. The EMF induced in the coil C in this manner is known as mutually induced EMF or an EMF of mutual induction. Okay. Other way we can say it EMF of mutual induction, or it's simply called as mutual induction. The important example of an appliance working on the principle of mutual induction is transformer. Okay. The best example of mutual induction is transformer, wherein we have a primary winding and a secondary winding, and that is wound on a iron core because we have to increase the permeability of the linking flux. We have to increase the permeability of the medium. If the permeability of the medium is more, then more and more flux will link from primary to secondary in a transformer, and hence the efficiency of the transformer will increase, which is, so the transformer is a static device used for changing the magnitude of alternating voltage. So here there is one important point, that if the primary turns and secondary turns, okay, so if the primary turns is less compared to secondary turns, then we can increase the voltage. By decreasing the current, we can increase the voltage, and similarly, by if the primary turns are more and secondary turns are less, we can bring down the voltage. Okay, this is the one of the important advantage of mutual induction, which is used in the form of a transformer. Mutual inductance: the two magnetically coupled coils A and C in the above mentioned example are said to have mutual induction. So as we have seen in this figure, there are two coils A and C, and we have understood by the procedure that because of the flux produced by current I in the coil A will link with the coil C, and an EMF is with the changing current in the coil A. Because of the changing current by varying the resistor, we have a magnetic EMF generated in coil C, which is seen with the deflection of the galvanometer. Definition of mutual inductance. So now we have to define what is a mutual induction or mutual inductance. Defined as the property due to which one coil or circuit with the change in its own current produces an EMF in a nearby coil by induction. Okay. So the definition is very clear. Here it states that as the property due to which one coil with the change in its own current produces an EMF nearby coil by induction. Okay. Due to the induction effect, due to the linking of the magnetic flux from one coil to another coil, and by changing the flux, we can induce an EMF in the another coil, nearby coil, and that is by induction, that is called as mutual inductance. Now we have to understand how much induced mutual induction induced EMF we can get, mutually induced EMF we can get in a transformer or in a two coils A and B, C here. With reference to the previous figure, whatever the figure we have seen here, with reference to this figure, we have N1 number of turns in coil A and N2 in number of coils in coil B. I is equal to current flowing through coil A in amperes. Phi1 is equal to flux produced by coil A due to I1 in it. Phi2 is the flux produced by coil B due to the current I2 in it. Okay. The whole of the flux, N1 is the number of turns in primary, you can call it as primary turns. N2 is the number of turns in coil B, which is the secondary turns. I is the current flowing through A in amperes. Through primary turns, if the number of current amount of current is flowing is I amperes. Phi1 is the flux produced in Phi1 is the flux produced in coil A because of current I1, and Phi2 is the flux produced by coil B due to the current I2. The whole of the flux produced by a coil does not link coil C. Suppose a fraction K1 of this flux is K1 Phi1, whereas K1 is less than 1 is linked with coil C, then Phi2 is equal to Phi1 into I1 Webers. So we have the flux Phi2 is equal to Phi1 into I1 Webers. If a small amount of flux K1 is linking with the secondary coil, then the amount of K1 is less than 1 is linked with the coil C, then phi 2 means the flux produced in the secondary coil is equal to phi 1, that is the flux produced in the primary coil, into the current flowing through the primary turns, that is in Webers. As already seen previously, any change of current in coil A changes this flux and thereby produces an EMF in coil C by mutual induction. The magnitude of this mutually induced EMF in coil C is given by the equation derived on Lenz's law, that is E2 is equal to minus of N2 into d phi 2 by dt. We can find the derivative of flux, secondary flux with respect to time, changing flux phi 2 with respect to time, and E2 EMF induced in the coil, EMF induced in the secondary coil is given by number of turns in the secondary coil and d phi 2 by d2. How much flux is produced or how much flux is produced in the secondary coil with respect to time is called as induced EMF, mutually induced EMF in the coil C. Hence, here the minus sign indicates that the induced EMF tends to circulate a current in the coil C in such a direction to oppose the change of flux linking with the coil due to change of current in coil A. It is clear that the magnitude of the current, direction of current flowing, since the here the EMF produced is a vector quantity, here we have a magnitude and also a direction, and the direction of EMF produced by the mutual induction is always in opposite direction to the current to the change in current flowing to the primary turns or the coil A. Now phi 2 is equal to phi 2 by I1 into I1. But if the permeability of the surrounding medium is assumed to be constant, then phi 2 is directly proportional to I1. Okay. So, but if the permeability of the surrounding medium is assumed to be constant, so if you consider a permeability of the medium as something constant value, then phi 2 is directly proportional to I1. Phi 2 by I1 is equal to constant, therefore rate of change of phi 2 is equal to phi 2 by I1 into rate of change of I1. So, if we change the current I1 primary current, then the flux produced in the rate of change of phi 2, the rate of change of flux phi 2 is equal to phi 2 by I1, which is the constant value. Now, here we have considered as a constant permeability of the medium into rate of change of I1. How much current is changing, that rate of change of I1 we have to consider. Therefore, from equation 2, E2 is equal to minus of N2 into phi 2 by I1 into rate of change of I1. So, by substituting the value of phi 2 in the previous equation, here we are substituting the previous equation, we are substituting the value of phi 2, and we can find that E2, that is the EMF induced, is minus of N2 by N2, we are finding the only the magnitude here. So, minus sign will not come here. So, N2 into d phi 2 by d2 dt, that is nothing but substituting the value of phi 2, we get E2 is equal to N2 into phi 2 by I1 into rate of change of I1. So, therefore, N2 is equal to this is equal to minus of N2 into K1 into phi 1 by I1 into rate of change of I1. The constant N2 K1 phi 1 by I1 in the above expression is called the coefficient of mutual induction. So, the coefficient of mutual induction without the minus symbol, N2 is equal to N2 into K1 into phi 1 by I1 is called as the coefficient of mutual induction, coefficient of mutual inductance, or simply mutual inductance. It is the quantitative measure of mutual inductance and is denoted by M. So, mutual inductance is given by N2 is equal to K1 into N2 into K1 into phi 1 by I1. Here the magnitude, we are considering only the quantitative aspect, and because of that we do not have any minus symbol, and that is give the coefficient of mutual inductance or just the mutual inductance of the coil. Hence the coefficient of mutual induction or coefficient of mutual inductance M of two coils can be defined as the flux linkages Weber turns of one coil per ampere current in the other coil. So, how much flux is linking in the secondary coil in Weber turns of one coil per ampere current of in the other coil, means for every per ampere current change in the coil, how much flux is produced in the secondary coil, that is called as mutual inductance of the two coils. That is given in Henry. The unit of mutual inductance is Henry because N2 into K1 into phi1 by I1 is the unit is Henry. Comparison between statically induced EMF and dynamically induced EMF. As we have understood in the previous presentation that dynamically induced EMF is the EMF produced wherein the coil is moving and the flux is stationary, whereas in the statically induced EMF the coil is stationary whereas the flux is changing or it is moving. So, in the statically induced EMF we have two types. One is self-induced EMF and mutual induced EMF. So, here it is clear from the previous presentations. Now, we have to compare what is dynamically induced EMF and statically induced EMF. Parameter, law which forms the basic of EMF production. Both the same, we have the Faraday's law of electromagnetic induction applicable for statically induced EMF and dynamically induced EMF. Method adopted to change the flux linking with the coil or circuit is for inducing EMF in it. Self-induced EMF and mutually induced EMF by changing the current. So, in the statically induced EMF, we are changing the current and we are varying the flux linking of with flux. We are varying the coil or circuit itself, and because of that we have the self-induced EMF and mutually induced EMF, which are nothing but the statically induced EMFs. But in the case of dynamically induced EMF, because of the motion of the coil, because of the movement of the coil from up down direction or any other direction perpendicular to the magnetic flux, we have the dynamically induced EMF. Expression for the magnitude of induced EMF: E is equal to L into di by dt volts, E2 is equal to M into di1 by dt volts with usual notations. Whereas in case of dynamically induced EMF, we have BLV sin theta volts. Okay. Then applications, transformers, statically induced EMF, we have transformers, induction motors, chokes, inductive coils used in fluorescent tubes, and filters used in rectifiers. Okay, then we have dynamically induced EMF, DC and AC generators, back EMF in DC motors. These are the applications of dynamically induced EMF. Coefficient of mutual inductance and dimensions of the coil. So, how does mutual inductance vary with the dimensions of the coil? Here the expression is derived here. M is equal to N2 into K1 into phi1 by I1, but phi1 is equal to N1 by I1 divided by L divided by mu A, that is N1 into I1 by S. M is equal to N2 into K1 by I1 into N1 into I1 by S is equal to N1 into N2 by S Henrys. So, how many turns are there in the primary and how many turns are there in the secondary divided by S. If the flux produced by the coil A links with the coil C, K1 is equal to 1. Okay. Here, if the total flux linking with coil produced in coil A links with coil C, then the K1 is equal to 1. That is the K1 is the flux linking with the coil, and M is equal to N1 into N2 by S is the expression given for coefficient of mutual inductions and dimensions of the coil. Coefficient of coupling. If how better it is coupled from primary to secondary, that is given here with the expression M is equal to root of L1 in L1 by L1 into L2. So, as far as coefficient of coupling is concerned, we have M is equal to N2 into K1 into phi1 by I1 M is equal to N1 into K2 phi 2 by I2. So we have two expressions for primary and secondary mutual inductance. So M square, because we know that number of turns is dependent on higher the number of turns, the square of the number of turns indicates the mutual inductance, that is M square. We have here M square is equal to N1 N2 into K1 into phi 1 by I1 into N1 into K2 into phi 2 by I2. So we are derived that K is equal to M by root of L1 into L2. So because we have considered K is equal to 1, because here total flux is linking from primary to secondary, there is no leakages. Because of that, M is equal to root of L1 into L2. So how much length of the coil is there in primary and how much length is there in the secondary, the mutual inductance is given by, coefficient of coupling is given by root of L1 into L2. The coefficient of the coils A and C can be defined as the ratio of actual mutual inductance present between the coils to its maximum possible value. So the coefficient of coupling of coil A and C can be defined as the ratio of actual mutual inductance present between the coils to its maximum possible value. How much maximum possible value is possible, means how much maximum possible mutual inductance is available, and at that instant of time what is the actual mutual inductance, the ratio of that gives the coefficient of coupling. So here with this we are clear that what is statically induced EMF, what is dynamically induced EMF, what is self-induced EMF, and what is mutually induced EMF. Here in both the cases, in the dynamically induced EMF and in the statically induced EMF, we have understood the magnitude or the coefficient of magnetic flux, okay, coefficient of coupling or coefficient of mutual inductance and self induction. Okay, here it is clear from the topic that how mutual inductance and self inductance are acting on a two coils or in a single coil in case of self induced EMF, and what is the magnitude of induced EMF that we have understood in the two slides in the previous two presentations. And here with this we have we are understood about the magnetic circuits, the basics of magnetic circuits. So here we, for example, the real applications of the magnetic circuits is transformers, which is a static device, and also a DC generator, which is a dynamic device. Dynamically induced EMF is generated, whereas in a transformer the statically induced EMF is generated. So with this we will conclude with the session. Thank you so much.